All right. Thank you. So, yes, I'm Ron, and I work at Oracle's Java Platform Group. That is the group that develops OpenJDK, where I'm the technical lead for Project Loom, which is the team that's devoted to adding threading-related features to Java. And I also have some experience with formal verification. I only used JPF more than a decade ago, but I am active in the TL8+ community, and the subject is near and dear to my heart. Right, so after about 5 years of work, we began at the end of 2017. Project Loom has finally contributed its first two major JEPs. There's a Java enhancements into JDK 19 that was released last month. The first is JEP 425. That's the JEP I'll be presenting here. And the second is JEP 428, structured concurrency, that helps combine or weave threads together correctly. Virtual threads are user mode threads that are lightweight enough so that a single Java process could have hundreds of thousands or even millions of them running concurrently. The purpose of virtual threads is to allow Java developers to write high throughput servers that make good use of available hardware while employing simple thread per request code that is harmonious with the design of the Java platform. This leads to readable, maintainable code that uses familiar APIs and supports existing tools like debuggers and profilers, all that without compromising on scalability. So what was the state of affairs before virtual threads? Java developers writing servers were faced with a dilemma. They could write code using blocking thread per request style, which fits very well with the design of the Java platform. We'll talk more about that. But it wasn't that scalable. It means that they had to waste money on hardware. They couldn't make efficient use of the hardware they had. Or another group of programmers got scalability by writing code in a different style, asynchronous style. But that asynchronous style doesn't fit well with existing libraries. It doesn't fit well with existing code bases, and it is very hard to debug and to profile. So they waste money on maintenance. To understand this dilemma and how it arose, let's first introduce the domain. And the domain we're dealing with is concurrency. And I want to first make clear what I mean by concurrency by contrasting it with parallelism. So parallelism is a problem of accelerating the performance of a task, meaning reducing its latency by splitting it down into multiple subtasks and employing multiple processing resources to cooperate in completing them. The source of the subtask is internal. The subtasks are created by the parallel algorithm. Concurrency, in contrast, is a problem of scheduling onto some sets of computational resources many largely independent tasks that arrive from the outside. The source is external. And we're mostly interested, the performance measure we're interested in is throughput, or how many of them we can complete per time unit. And servers are a canonical example of concurrent programs. Virtual threads are largely aimed at implementing servers because servers are a major use case for Java. The throughput and latency of systems like servers is governed by an important result in operations research called Little's Law. It says that the long-term average number of work items, that's L, that are concurrently present inside. So we define some borders, and that's a number of things inside. So the long-term average number of work items or requests inside the system is equal to the average long-term duration W that they spend inside it times the average request rate or throughput. A stable system, I said it applies to stable systems. Stable system means one where there is no ever-growing queue that forms at the entry to the system. And because the system is stable, we know that the request rate is equal to the exit rate or the throughput. Otherwise, there'll be an ever-growing queue. Now, the result is actually not trivial to prove because the interesting thing about it is that it is independent of any statistical distribution of these variables. It is dependent only on the average regard, and it's true for any distribution. Next week, I'll be giving a talk at the P99 conference, a conference devoted to software performance, where I'll talk more about Little's Law and its implication in more detail. But for now, we'll just tie it to threads by explaining what thread per request is. So thread per request model, let's define it, is one where an incoming request to the server consumes at least one thread for its entire duration. So that's a W. For all of W, the request consumes at least one thread. And it is a very natural way of writing server programs because it represents the domain unit of concurrency, the request, by mapping it directly onto the software unit of concurrency, which is the thread. In that style, when we wait for I/O, we block the thread and hold on to it until the operation completes and returns. Now, this means that according to Little's law, the number of threads that will be required is going to be L. So the higher the throughput, the more threads are needed. Or conversely, the number of threads, the maximal number of threads places an upper limit on the attainable throughput. Now, if requests consume just CPU, then the number of them that could make progress concurrently, or L, would be equal to the number of processing cores. But that is hardly the case in most servers. Most of the time, requests wait for some outgoing I/O operations, like a query, database query, or an outgoing call to some other service. So many more of the requests can make progress by waiting than we have calls. And the problem was that traditionally in Java, a thread was just a thin wrapper around an OS thread. And now that we have a new implementation of threads, we've taken to calling these traditional threads platform threads. So platform threads are Java threads that correspond one-to-one to an underlying OS thread. For various reasons, the OS cannot support too many threads at any one time. Only a few thousand, or perhaps 10,000 of, and I'm talking about active threads. This means that threads, depending on throughput, are exhausted long before other system resources like the CPU or network connections. So our maximum throughput is capped by this limitation. And that means that we're not making good use of the hardware, and we need to waste more hardware. Interestingly, though, the Java specification does not, and never did, mandate that this is how threads should be implemented. In fact, in very early implementations of Java, before the advent of threads in every operating system, they were implemented in user mode. But it sort of gave us, it's like the assumption that a thread is actually an OS thread is not something that is built into Java. So platform threads, we can't have many of them, and that places a limit on throughput. So what do other people do? People who don't want to waste machines turn to asynchronous programming. And asynchronous programming does not process a request start to finish on a thread. When they use a thread when they're using the CPU, but when the code that handles a request needs to wait for I/O, instead of blocking and waiting while hanging on to that thread, they return it to the pool and reuse it for other tasks. So the number of requests that can make progress concurrently can be much greater than the number of threads. So that L from Little's law is not limited by the number of threads. But even for programmers who are comfortable with that style, and many aren't, it suffers from some fundamental limitations because it is disharmonious with the design of the Java platform. For one, it is viral. It is all or nothing. You need to make the entire application asynchronous, and that requires using a completely new set of APIs. And worst, we lose the ability to easily observe, debug, and profile the application. And that is because the Java platform is built around threads. From the language, through the libraries and the VM, and all the way to the tools, the platform is organized around threads. So I'm not talking about, it's not that the asynchronous model is necessarily bad in general. It's just sort of incompatible with the design of Java. The language's basic constructs of statement sequences, the sequential composition, loops, method calls, exceptions are all confined to a thread according to the Java specification. Exception stack traces give us troubleshooting context in the form of a thread's call stack. We use thread locals to give operations implicit context by attaching data to a thread. So there's sort of an assumption that a thread is your context. When we debug, we step through the execution of a thread. Profilers group events by threads. And we lose all that when we abandon the thread per request model in favor of asynchronous code that sequences, that composes operations sequentially, not on the same thread. Enter virtual threads. Virtual threads are Java threads. They are represented by the same Java lang thread class. They pass the same specification. They have the same behavior. They have the exact same semantics, but they are implemented in user mode by the Java runtime. And the Java runtime can implement threads in a manner that allows them to be much more plentiful than the OS. And part of the reason is that, much of the reason is that the Java runtime knows how Java code works. In particular, it knows how Java code uses a stack. So instead of having huge stacks that are fixed in size, we can have resizable stacks that grow, and that you can also do with virtual memory, but they can also shrink, and their granularity is like that of a word. It's not a page. The OS only works in pages. And we also have context switching in user mode, and we can pick our own scheduler that is optimized for transaction processing. But in terms of semantics, they're the same as threads. So the way they work is that we have lots of virtual threads, and under the covers, the Java runtime runs in user mode, so we can't directly schedule them onto CPU calls because we're not the kernel. So we sort of approximate the CPU calls with OS threads. So the scheduler maps virtual threads to OS threads transparently. How we do? Virtual threads require much less memory because of those stacks that grow and shrink. So we can have many, many, many more of them. And as a nice bonus, context switching is also faster. But the most important thing is the number. This is something that developers in industry often don't understand. It's something that we're trying to explain to them. The important thing that gives virtual threads or user mode threads in general their performance, which is throughput, is not that they're faster, and it's not because their context switch is lower. It's just because that they can be more numerous, and due to Little's law, that translates to higher throughput. And so by having lots of threads, and those behave like today's threads, users can write code in the thread per request style that's harmonious with the design of the platform, without placing an artificial software limit on throughput. Throughput is only limited by hardware resources. And to see Litter's law in action, we did an experiment with a Jetty web server. That's a popular web server written in Java, where we simulated a transaction that spends 100 milliseconds, or 1/10 of a second, on I/O. And we see that, just as the formula predicts, when we have 200 threads, that's the blue line, our server maxes out at a throughput of 2,000 requests per second. So L is 200, because we have 200 threads, and that is equal to 2,000 requests per second times 1/10 of a second per request. And what happens after that point, when the equation no longer holds, the system becomes unstable. That means a queue starts to form and the server essentially crashes. With 800 threads, we cap out at 8,000 requests per second. But with virtual threads, we just keep on going. That's the y-axis is the latency of every request. And we can keep increasing the load until we exhaust the hardware, but we didn't have enough hardware to exhaust the servers. Right. Here's an example of using a virtual thread to download a web page to a local file. The examples is really boring. There's nothing new here, except for this new method to. So when you create a thread, you need to say, do you want it to be virtual or do you want it to be a platform thread? And the APIs here are the good old synchronous I/O APIs that existed in Java for 2 decades. But under the covers, and completely transparently, we just when we block on I/O, we actually release the OS thread and schedule another virtual thread in space. We'll talk more about that in a moment. Now, it is a huge feature of virtual threads that users don't need to learn any new concepts here. And in fact, we've considered that for a while. Do we want to use the same thread abstraction or introduce a new one? Ultimately, we came to the conclusion that it's better to just use the existing one. But even though virtual threads are just threads, the form factor that they can be so small and numerous. If you want to do 2 tiny things in a method, just start new threads and then join them. It's free. And because the form factor does matter, users have to unlearn some old habits they developed to cope with the high cost of the traditional platform threads. For example, virtual threads should never, ever be pooled, just like we don't normally pool strings. So there is a pedagogical challenge here, because those habits are well ingrained, and sometimes people don't understand that they only adopted them because threads were so expensive. Now that it's kind of hard to get accustomed to something that used to be so expensive suddenly becomes essentially free. Okay, now I'd like to spend some time on how virtual threads are implemented under the covers. The implementation of virtual threads is based on a powerful and general construct, delimited continuations. More specifically, they're going to be non-reentrant or single shots, delimited continuations with multiple named prompts. That is the academic designation of the kind of delimited continuations we have. I'll show you what that means in a moment. But if you don't know what delimited continuations are, they are just computations that can suspend themselves and later be resumed. We implemented delimited continuations in the hotspot VM. That's a virtual machine of OpenJDK, where their state is stored in the Java heap. A significant engineering challenge was to, on the one hand, find a way to capture and resume the state to and from stacks that can grow and shrink, and on the other hand, not to actually copy the entire stack of the computation back and forth. So I'll show you how stacks are copied, but that is sort of a logical view. They're not actually copied, or very small sections of them are. Another challenge was how to let the GC traverse all the pointers in the stack while not making them GC roots. The GC roots are sort of where the GC starts, and platform thread stacks are GC roots, and they're handled in a specific way. But now we have millions of threads, and the GC doesn't like having too many roots, because modern GCs in Java, if you know, we now have worst case pause time of under 1 millisecond on heaps up to 16 terabytes, I think. So they've gotten very, very, very good, but they don't like having too many roots. Now, much to the disappointment of some bleeding edge developers, and sometimes even ourselves, that is often the difference between working in academia and in industry, we've decided not to expose continuations as a public API to users, because while it is a very general and powerful and academically interesting construct, it could allow libraries to subvert invariants that much Java code depends on. For example, that the identity of the current thread doesn't change in the middle of a method. And as soon as you give developers any power, they'll start using it to do the craziest thing right away. And we have to be careful with an ecosystem as big as Java. So this magic has to stay under the hood for the time being, at least until it can be tamed somehow. But we can use continuations as an internal building block for building valuable JDK constructs on top of it, as we've done with the virtual threads, and perhaps others in the future, like generators. So continuations are not exposed as a public API, but this is what the internal JDK internal continuation class looks like. Continuation has a body, it behaves like a runnable, it implements a runnable, and you can run it, but it can also yield itself, which suspends it. So when you run it, it will run up to the call to until the time it finishes, or until the call to yield. When you call run again, it will continue from the last yield point. So it's stateful, that's why it's called non-reentrant. The scopes, I might mention them a bit later, but they just allow us to nest continuations. You can ignore those for now. Right, so this is just to give you a sense of how they would work. So this would be the body of a continuation, prints before, then we yield, and then we print after, and we call continuation run, and we'll just print before. The second time we call run, we'll print after, and then is done is going to be true. Okay, so that's continuation. But what is a thread? A thread, what is a thread made of, rather? So a thread needs two capabilities. It needs a capability to suspend and resume a computation, any kind of thread, even in the OS. And it needs a mechanism that decides when to assign those computations to execution calls. And those two components are a continuation and a scheduler. When it comes to virtual threads, we implemented that continuations in the hotspot VM, but the scheduler is implemented in Java in the JDK libraries. So the continuation part doesn't deal with concurrency at all. It's like a runnable, it is single-threaded. All the considerations of concurrency are taken by the scheduler, and it's written in Java. So we had to essentially change all the places in the JDK that work with threads to support virtual threads like you want them to, but it doesn't sound as scary it's not as scary as it sounds, because in most places, except for very old IO libraries that were written in C, and we sort of rewrote them in Java, when you want to suspend a thread, you normally end up in this method, Java utility concurrent lock support park. And all we had to do there is to say, if the current thread is not virtual, then call unsafe park, which does a syscall to the OS to suspend the current thread. But if it is a virtual thread, we are running inside a continuation, then yield it. when we yield the continuation, it's sort of the task that's running that runnable appears to return, like we showed here. We call run, it returns. The scheduler doesn't even need to know that it's running a continuation. It's like, okay, that task is done. So this is used to implement all the concurrency constructs in Java utility concurrent and most of the I/O now. So what happens? We have on the scheduler thread, we call it the carrier because it carries the continuation or the virtual thread on its back. So we are running scheduler code. By default, we use a fork join pool, which is a work stealing scheduler that's been in Java for many years, but it's been adapted a bit to work better for virtual threads. And we just pick a task out of the queue and we run it. But what we are running is a virtual threads continuation. And we start running it. And this is going to be the task this is the body of the thread. And it's going to run until it reaches the call to accept a server connection. So this is a server and it's waiting for a connection. It's going to make some calls, and in the end, it's going to reach that method I showed you. Here it's called a bit differently. The slides are not synchronized, which is unfortunate when talking about synchronization, but still. And that translates to a call to continuation yield. When yield is called, those frames, it could be, there are many frames inside accept, a lot of logic, TCP logic, I don't know what's going on there exactly. Those frames are removed and logically copied from the stack into the heap. And then we return back to the scheduler, which will pick up another task from its queue and run it, which might well be another virtual thread. When the operation is complete, so an I operation is complete or a lock is released, all those work sort of the same way from this mechanism. You have a code path that ends in you parking and some other code path that unparks your thread. So the call to unpark, some other thread says, for example, we do an asynchronous I/O in the background, and we have some polar in the background that does asynchronous I/O. When the operation is complete, it says, I want to unpark that virtual thread. Or you have thread that is owning a lock, and now it wants to release a lock. So the code of the lock will say, who are the threads that are waiting for me? And it will say, okay, I'm going to unpark them. And in fact, it doesn't need to know if the thread is virtual or not. It's just, there's an abstraction. Inside unpark, as in park, we do care. We open up the abstraction and say, okay, if you are in a platform thread, we're going to call the OS. But if you are a virtual thread, again, this is an old version, it should be is virtual. We've tried many different names. All we do is we take the thread's continuation and submit it to the thread scheduler as a task. So the next time the scheduler, this makes the thread runnable. When the scheduler gets to it, it's going to run it. But running a continuation means continuing it. So what's going to happen is we get a signal from the OS, we submit the virtual thread's continuation back to the scheduler, say it calls run again, and that mounts, we call that operation mounting, it mounts a virtual thread on the scheduler's carrier. It could be a different carrier, it doesn't mean to be the same OS thread. It sort of pages back the continuation frames from the heap and then returns from the I/O operation. So while the code appears to the user to be doing blocking I/O on its own private thread, the runtime actually converts it so that from the OS's perspective, it appears that one of a very small number of scheduler threads initiates an asynchronous I/O operation, then does something else, and then goes back to handling the results of the operation. So the user writes synchronous code, but the OS experience is it becomes translated automatically to asynchronous code. The user cannot perceive that the underlying carrier has been swapped out. They only see the virtual thread they're running on. As I said, in reality, we don't actually page in all the stack frames if we don't need to. We sort of do it lazily so that the cost is independent of the depth of the stack. Okay, so now we get into virtual threads and formal verification, and it's sort of, I don't have any bad news, but I don't have any good news. Maybe we could present it, maybe we could put a positive spin on it. So on the one hand, the semantics of virtual threads are identical to platform threads. Java code, in terms of the specification, Java doesn't care whether a thread is virtual or platform. Everything when it comes to the memory model, all that are identical. So say model checking, 2 virtual threads and 2 platform threads could be done exactly the same way. And of course, nobody can model check unless, I don't know, you've onto something amazing. Nobody can model check 1 million threads anyway. So we're normally talking about a small number. So it just doesn't matter. But I think it might make life easier because it means that fewer people will use asynchronous code, and I can't imagine that asynchronous code is pleasant to model check. Also, the throughput benefits are when the throughput can enjoy a great many threads. And when you're doing some batch operation that is CPU heavy, you know, like, I don't know, computing states or SMT solving or something like that, more threads and CPU cores won't help you. So they don't, I think, help in the implementation of, say, model checkers. But in the future, we plan, in the near future, I think, we plan to have, I mentioned that the schedulers are written in Java, and that means that users could implement their own. The reason we haven't done that yet is partly because there were some problems in the VM that we had to solve, but also because when you get your earliest adopters are usually the most advanced users, and they want to do the craziest thing right away. And we thought it would distract. We're trying to get into people's mind. Virtual threads are threads, but you can have lots of them. Just use them with the default scheduler and see how great they are. In the future, you'll have custom schedulers. So custom schedulers mean that every time you go, the virtual thread, the continuation goes back to the scheduler, your own code can decide what to do. And in fact, here's a blog post of somebody who sort of hacked into the internals and did use the internal classes to write a deterministic simulator for semi-exhaustive simulation of the raft protocol. So I do think there is something interesting there for not just formal verification, but let's call it the quality assurance in general, community in general. So keep an eye out for that. Last thing, yeah, so current limitations. There are situations where we cannot yield a continuation. We cannot remove it from the carrier's stack. If one of the stacks is native code, of course, native code can contain pointers into the stack, and it is not movable in memory. This is given, you know, Rust code and C++ code that tried to do continuations a great deal of trouble. That's why they had to do something else. In Java, it's not much of a problem because it's quite rare. The more serious problem, but one that I hope is temporary, is the use of native monitors. Native monitors are synchronized blocks or methods. So if you're trying to do a blocking IO operation that would normally unmount the virtual thread and yield a continuation, we can't do it if any of the frames inside the continuation is inside a synchronized block. We hope to fix that. If it happens, read, there are more details about this in the JEP itself, shows how to diagnose it, what to do. It's hard to, it's quite easy to work around. You just use Java util concurrent locks. Yeah, it is annoying for the moment, but hopefully not too much. But when that happens, so what happens when we pin and we try to remove the continuation? If we fail, we just block the underlying OS threads. And in some situations, we compensate by creating more scheduler threads. I mentioned that we want to add custom schedulers as well as generators. So generators are sort of an imperative way of writing iterators. So you write sort of a for loop that says yield, and every time you yield, it returns to the caller another result. And that is also commonly implemented using continuations. And because we have nested continuations, we could have generators inside virtual threads. And inside the generator, you could do, to generate the next element, you could do blocking IO. And in that case, you would yield the generator's continuation and the enclosing virtual thread continuation. Anyway, that is that for me. If you have any questions.